Thank you everyone for being here. So yeah, I'm trying to explore a little bit some of the enigmatic mineralization styles that exist around Sudbury and try to provide a framework as well to explain why do we see such mineralization type, alteration zone, and then some tools potentially to explore them as well based on their characteristic. Okay, so just cautionary statements, a forward-looking statement might be made in this presentation about the public issuers. Just be warned that they may not be realized in the future. And then that's the outline of the presentation. So first, we're just going to do a brief overview of what is a MIC system. It's a relatively new concept. It has been introduced a couple of years ago, and it really helps to frame some of the Canadian but also international context where there is polymetallic mineralization and really explaining why can we see such diversity of alteration and mineralization type in certain geological provinces. And then what we'll do after is we'll apply these concepts to the southern province around the Sudbury area and present some of the exploration strategies and the next step that Canuc Resources is pursuing to explore the East Sudbury project. I would like to, when we start this overview, I would like to briefly acknowledge, because this is part of the research, scientific research that I've been doing through the years on these systems. So all the collaborators that helped and supported and contributed to the development of the concepts that will be presented, as much from the private, public, academic sectors, and specifically Dr. Louise Corriveau from the Geological Survey of Canada, because a lot of that comes from her vision and also her leadership in order to define and characterize those mineral systems. So what is a metasomatic iron in alkali calcic mineral system? So initially, or before, we used to call those IUCG system or a bunch of derivatives that were routed back to IUCG system. But using only IUCG makes it sometimes a little bit difficult either to frame or to fully grasp the full diversity that can exist in those crustal scale metallogenic system. So we transition towards MIC as a better reflection of the geological processes that controls their formation, and also some of the key characteristics of alteration that are the results of these fluid rock interaction that happens over hundreds of kilometers in the geological province. So metasomatic really characterize the fluid rock interaction and the products of that. So you can completely transform a rock, regardless of its composition, and completely re-equilibrate its mineral assemblages because of very intense fluid rock reaction. Iron, because it's really ubiquitous in all the on many of the alteration zones that are being formed in those systems. So in general, it will be iron-rich system, and they'll lead to the formation of iron-rich alteration type. One thing that's important is that we need to be beyond the iron oxide. So in many instances, the mineralogical expression of iron-rich alteration will be iron oxide, but depending on the composition of the geological sequence and also some characteristic of the fluids, iron sulfide, iron silicate, iron carbonate is also possible. So iron is important, but iron oxide may not be the only mineralogical product of these fluid rock reaction. And alkali calcic, because generally when there is an iron-rich alteration, iron will be coupled either with an alkali or a calcic component, and this combination between iron and those elements can help to understand where do we sit in the evolution of the system, and also potentially prognosticate what type of metal assemblages can we see. So the alkali element will be primarily potassium and sodium, and also alkali because large amount of alkali alteration can exist in those systems. The example are the corridors of sodic alteration, which can lead to the formation of albite. And then calcic, so calcium, magnesium, barium, because very often we see those coupled with iron. But also now what is emerging is that as much as there's a suite of iron-rich alteration type, there's also a suite of iron-poor alteration type. And in general, these iron alteration type, and these are particularly applicable to some part of the southern province, will have this alkali calcic signature in relationship to mineralization. Oh, it doesn't show. Okay. So when we talk about intense fluid rock reaction and metasomatism, so it's really a complete transformation of a rock, as much its textures, its structure, and its composition. And I use here an example of a siltstone because I felt it could be applicable to the sedimentary context in which we are working with. So we take a siltstone with its bedding visible, and then once we transform that siltstone into an albite, everything is gone. So we're transitioning from a biotite rich rock, which has some plagioclase or minerals, and then we end up with something that it's almost composed uniquely of albite and quartz. So a complete reequilibration of the composition, but also textural and structural change as well to go from the siltstone to the albite. We'll be talking a little bit in the presentation about alteration facies or alteration type, can be used as relative synonyms. So why we use this concept? We use this concept because when you reach a certain stage of evolution of the system, many different assemblages of minerals can be formed. So if we just look at the assemblages of minerals and we try to map those, it can become extremely difficult to make sense of that because certain areas will have more amphibole, other area can have more magnetite, and there can be, so using this example here, so all these permutation can create a relative chaos trying to figure out exactly where do we sit in the evolution of the system. But grouping all the mineral assemblages that are formed approximately under the same condition as alteration facies, it really helped to make a cohesive framework after to map these variation and assemblages of mineral and assign them to the same evolution stage of the system. And it makes it a bit more understandable, especially when we look at cross-cutting alteration and many different assemblages of minerals. And using these alteration facies, so this figure is a little bit complex, so I will take a bit more time trying to make a framework of it, is that when we look at an IMIC system in general, what we've been able to establish is that these systems are forming multiple alteration facies, and that each of these alteration types of facies, there can be metals that will be concentrated because the fluid in the system evolves compositionally and the temperature changes as well. So necessarily different assemblages of metal can be precipitated as the alteration forms. And then identifying these alteration facies can help us to define, okay, so which assemblages of metal are the most likely to be present in zones of alteration or mineralization. So if we start from the initial eating state, that's when we're going to form out of the sodic alteration. So we can also replenish the fluid with all the elements that are being eaten from the host rock. And then progressively, the system is going to evolve, reaching its thermal peak at the high temperature calcium iron facies, and then progressively cool down. And with that, we can form different mineral deposits, each with their own assemblages of metal. There are two groups as well of alteration types that form mineral deposit. One group that is iron rich, so it goes from the number 2 to 5, B, and then one group that doesn't have the iron but can still form some metals, so the more alkali calcic alteration type, and these ones are at 5C. So just to provide a visual illustration of the diversity, so right here we're looking at the iron-rich alteration type. So we have a huge diversity of mineralization type that can be formed, but there's a general association between a specific mineralization type and an alteration type or alteration facies. So we go from iron to iron with rare earths, to iron with nickel, to iron with cobalt. It can be iron oxides or iron silicate, depending on the context. The classic IUCG type mineralization, so iron oxide with copper. But IUCG mineralization, so iron oxide with copper, is one of the mineralogical expression that can be related to other environment. We can have iron sulfide with copper, so this will form iron sulfide copper gold deposits. So for the southern province, this could be important in certain areas, or we could have also iron silicate coupled with copper and gold, which will form iron silicate type copper gold mineralization. And also for geological environment like the southern province, the concept can also be important. This example is actually from the Temagami area, the one to the right there. Oops. And then other examples, iron oxide, uranium mineralization and placed in an albitite. So it becomes albitite also iron oxide, uranium. And then the example from scattering, so we have gold with iron silicate, an iron silicate gold type of mineralization. So quite a diversity of mineralization type associated with specific types of alteration. And then we have the iron pore component. These ones are not as studied or as well understood because in general, they were not, or the relationship between the MIC system and these type of mineralization was not completely established, but more and more now there are clear evidence that there are indeed part of the same hydrothermal system. They just form in different zones from the iron-rich counterpart, or they can be relatively close as well. So there's a lot to learn about those, but some things that we start to see that there can be uranium gold, in this case, overprinting in albite. So this is from the Romanée hoist in Quebec. As an example from the southern province, which we'll discuss a little bit more, gold and brecciated albitite, gold in veins forming over an albitite, and then copper gold in relationship prime to carbonate and carbonate quartz type of alteration. So if we move in the Sudbury area, so we keep some of these concepts in mind, so we can have a large hydrothermal system that will be structurally controlled, can form a wide diversity of mineralization type. So how can we apply this to the Sudbury area and also to the East Sudbury project of Canuc? So when we look at the structural context of the property and also where it sits in relation to the Sudbury Basin, so we have the Sudbury Basin on the right side of the image. And in pink, what is being outlined are structural corridors that are associated with polymetallic and gold-bearing showings. So really removing every showing that seems more related to the Sudbury-Igneous complex, but and focusing on the showings or zones of mineralization that are more likely to be hydrothermal or controlled by hydrothermal process. And when we move west of Sudbury, a lot of alteration mineralization seems to be related to the Murray Lake fault system. Then that corridor is kind of merging with the Grenville front. So we have the Long Lake gold mine at the western part of this. And then where the East Sudbury project is located, it's kind of a structural confluence between many corridors of mineralization. So we have the probable Murray Lake fault, which kind of merges with the Grenville front, the McLaren Lake fault, which is a northwestern structure, and then the Laundry Lake structural corridor is actively explored by Ventus to note of the East Sudbury project. And then there's also a clustering of the metallic and gold-bearing showing, especially associated with this area. There's a couple historical producers, so some of the main ones primarily for gold, the Scadding gold mine and the Long Lake gold mine. And then with copper as well, there was the North Star copper gold, which is not on the East Sudbury project, but it's located in a gap within the clay fabric. And when we look on the property itself, well, there's many important structural systems, and we'll cover them a little bit in the presentation. If we look about the timing and what is the general geological context for this event, so the Southern Province has a very long geological history, and there's multiple periods of metal deposition that happen. And the event that would have formed the MIC system would be in one of the latest important event in the history of the Southern Province. This corresponds with the emplacement of many intrusive suite. It's an active tectonic environment. It's an orogenesis that happens as well, and there's a lot of metamorphism and deformation that is dated within that time period. And there's also regional alteration and especially sodium metasomatism. So it will be around 1740 to 1690 that the MIC system would have been developed in the Southern Province based on the ages that are currently available through the literature. And one of the key indicators as well is the ubiquity of soil alteration. The OGS did a lot of work in the 1980s, 1990s, and there's been a recognition that outside the Sudbury Basin, when we look around, there's a very good spatial association between the development of sodic alteration, which can form albitite, and overprinting mineralization. And the sodic alteration has been traced at least from Temagami to Bruce Mine. So when we move west of the Sudbury Basin, primarily in relationship to the Murray Fault, and then once we move east of the Sudbury Basin, the structural control becomes a bit more polydimensional, but it's a long corridor of silicic alteration that takes over 240 kilometers. One thing that remains an impediment is that albitites, as geologists, we're very good to name them a lot of different names of what they are, albitites. So very often there'll be chert, there'll be quartzite, there'll be orangefield, there'll be sienite. A lot of times we see them, but we don't name them. So there's potentially more albitite as well that were actually recognized or described in the past because of some challenges in recognizing those rocks. And I did that a couple of times myself, naming sodic alterations on the silicification because they're very hard, they're homogeneous, they really look like silicification, but sometimes they're not. They're actual albitite. And this is a good example down there of a an albitite from after the Serpent Formation. It's a very homogeneous rock, but it's not silicification in this case, it's sodic alteration. If we zoom in on the East Sudbury project, so as mentioned, there's a interesting adjustment of structures. So this property had a very long structural history, and working with Goldspot, we were able to identify structural domains on the property that was very useful to help understand the structural and geological framework for some of the mineralization type, and also what structure with which age, and that right? And using this work, we're able to identify so different structural domain. So name number 1 to 4 on this image. Also different structural corridors. So some domains where there's an interaction between Grenvillian formation and Yavapai structures. So structures at 1700 million years, structures primarily at 17 million years, and then structures that be older than that. Maybe their metallogenic potential and relationship the that we're looking at may not be as significant. And in terms of the Yavapai, so 1700 structure, the main ones were the Murray Fault, the Grenville Front, the McLaren Fault, which those are all in the Alwyn prospect, Bug Lake Fault, which is related to the Scadding and Glade gold showings, and then the Washagami Fault, which hasn't seen the same level of exploration as the other ones, but they have a high structure, so it could have also an interesting metallogenic potential. And you start looking at some of the mineralization that we have, the Sudbury project, and to frame them within the MIC context. So if we look first at Alwyn, so the Alwyn prospect is located at the northern end of the McLaren Lake Fault just before it goes under Lake Wanapitec. And the McLaren Fault is interpreted to be the main structural control on that zone of mineralization. There's a couple additional copper gold showing along the McLaren Lake Fault that includes the Igami copper gold prospect and the Carrera showing, which is located at the southern end of the trend before the McLaren Fault is probably rotated and then transposed in Grenvillian deformation as it moves closer to the Grenville front. All was selected as a drill target in 2022. It was the collaboration with the work of Gold, and as much internally as spot, this was one of the highest priority target in order to find good mineralization. And we indeed find good mineralization in 2022, and we followed with a small drill program as well in 2023. So what did we find at Alwyn? So the host rock that will be presented on all the following pictures is a Goganda conglomerate or different variants of the Goganda conglomerate. Then we observe a strong abnormal system with polyphase alteration, some of which are associated with copper gold mineralization. So we observe iron power alteration related to copper gold mineralization and also iron rich alteration associated with copper gold mineralization, in addition to new types of iron alterations that were not recognized or identified in the area before, and also areas of sodic alteration. And we'll come on to the map a little bit later, but just draw your attention on the corner to the top of the figure. This is where the drilling happened in relationship to the McLaren Lake Fault, which we can see marking a clear contrast between areas of different magnetic intensity. So when we look at sodic alteration, very classical visual expression. So we see the Goganda conglomerate progressively outlies at variable intensity up to formation of albitites. Was not completely known before that this was affecting this area over such an extent like that, but now we see that there are strong and intense sodic alteration within the Alpine area. And then that I would say that one of the key targets and something that we wanted to explore back in 2022, we didn't really knew what we were going to get, but what we found was a target that we named the Alwyn 2 vein. So it's dolomite or ferro and dolomite with quartz vein mineralized with chalcopyrite. There is an example in the core boxes there. And this is likely, so there was an historical ground development at Alwyn. You can see the drill holes are all around it. It was likely the historical target when they were attempting to mine there. I think it was back in the 1930s. But one thing we realized as well is that more than the vein, there's a very large epithermal system developed on the vein. And on these drill hole, I plotted copper over 500 ppm to show that there's the vein, which grade good copper, but there's also a broad copper anomaly surrounding the vein. And part of that copper anomaly in the immediate vicinity comes from a network of veins positionally similar to the 102 vein that are also mineralized with chalcopyrite. So overall, there is a higher grade domain centered on the vein, and then there's halo related to this multidimensional network of veins. They have different orientation. One thing that really started to get interested, so we found the vein corresponded to what was historically known about the area, or at least some of the knowledge. But when we started getting deeper in the system, there's been a mineralogical position and changes as well in the type of alteration. So we started finding the first conclusive evidence of strong potassic alteration. So potassic alteration that gets into the 8-9% potassium when testing that with PXRF, so close to getting a lot of KFAR. And also relationship between some of that potassic alteration and copper mineralization. So now we're not only having carbon quartz vein, also having a potassic component that shows a specialization with copper mineralization. In addition to relics of the sodic alteration being overprinted by some of these alterations. So the images at the bottom, they're micro XRF images, and there are imaging different elements that are with these rocks. So we can see in pink on the image to the left, the relics of the sodic alteration, whereas the green on the image in the middle would be the potassium, and the purple would be the copper. And also, what our drilling, the drilling in 2023, not in 2022, started to define as we moved out progressively away from the historical mine, indication of iron-rich alteration related to copper mineralization. So in this case, we have an iron silicate assemblage where there's garnet amphibole in relationship to chalcopyrite. Also, the development of that, we named it dark chloride. Mineralogically, we haven't looked at it under a thin section, so we're not sure. So we named it chloride alpha identifier. Also coming with a little bit some of hematite in relationship to the chalcopyrite. And another alteration type that became extremely interesting as we move quite far away from the all or the spherical underground development itself is the identification of pervasive magnetite alteration in the conglomerate. So the conglomerate, it's matrix, the Goganda conglomerate, it's pervasively replaced by magnetite. Visually not very obvious. You can see on the core pictures there. So the non-magnetized conglomerate is a bit more greenish, whereas when this pervasive magnetite replaces it, it becomes a bit grayish with the replacement of the matrix by iron oxide. Still form strong magnetic signature. So we detected it actually just by doing systematic magnetic susceptibility measurements because visually it's not easy to pick that up. So the mags picked it up. And then, okay, so yeah, there's quite a bit of magnetite alteration. And then for also forming 3 zones, so that the whole had 3 separate zones of magnetite alteration with an intensity is higher than the diabases that were forming this intersection. What's interesting is that we're sitting at the edge of a magnetic high there where we start to pick up that hydrothermal magnetite alteration. So now there might be a correspondence between some of these magnetic high and hydrothermal magnetite. Initially, the idea was that this would be related to diabase, but now there's a good probability that it's actually magnetite alteration, which is causing this magnetic signature in the geophysical surveys. Uh, Additional visual expressions, sometimes pervasive replacement are not easy to trust the leaf, but when we start seeing magnetite veins or class selectively replaced by magnetite, also very good conclusive evidence that there are actually or oxide alteration in this part of the system. And the other component that came to be interesting is that overprinting of magnetite alteration is the element now it's incipient, so it's at probably the edge of something potentially, but veins of cobalt chloride or cobalt chloride with K feldspar in relationship with copper mineralization. There's chalcopyrite with amphibole chloride and sometimes feldspar. So an iron silicate type of alteration that comes overprint these areas of magnetite, again sitting at the edge of these geophysical target. And when we start integrating with the structural picture that we have for Alwyn in different layers of geophysical surveys. So we have in red, these are gravity anomalies. So there's an interesting alignment of gravity high along the McLaren Lake Fault, but also when we have intersection of the Laundry Lake Fault, which is known to be mineralized as well with the work that is being done to the north, then there's a state of gravity high that align close to these intersections between the McLaren Lake Fault and the Laundry Lake corridor. So there could be a potential that some of the gravity high relate to the intensification of the iron rich alteration type, which now there is evidence that they're associated with mineralization, and then potentially finding something buried there that have affinities with iron oxide copper gold mineralization, but in this case, the possibilities are that it's going to be silicate copper gold mineralization for this geological environment. Another target that exists or is present on the property. This is really the one that started making the connection with systems that come from IOCG. So it's the iron-rich mineral alteration related to gold mineralization at Scadding. And also now we are able to extend it to Lake. So Scadding is located in the middle of the property alongside the Bug Lake Deformation Structural Corridor. It's a historical producers. It's been discovered in 1973 during a uranium survey because there's also a low uranium, very low, but still uranium anomaly in relationship to the chlorides of Scadding. If we look at the geological context of Scadding and Glade, it's actually interesting because even though they're separated by approximately 800 meters, there are similarities on the structural and geological controls for two zones of mineralization. So in yellow, it's the Serpent Formation. In blue, it's the Espanola Formation. So Scadding is located very close or at the contact between Espanola and the Serpent. And it's likely that Espanola acts as much as a rheological buffer to enhance the formation, as much as a chemical trap to help precipitating the gold. And then blade, located to the south, is located at the contact between a Nipissing intrusion and the Espanola Formation. So very similar geological environmental formation for both zones of mineralization. At the alteration sequence at the scattering deposit. So it starts like many other showings in the southern province as with some alteration progressively evolving to albitite. Sometimes this alteration is going to evolve to these furrow and dolomite formations. So it's actually sometimes very spectacular, can form very large crystal. And these crystals are the product of the in-situ replacement of the rock. So it's not open space filling. It's dissolution precipitation forming these furrow and dolomite. And we can see that by doing the micro XRF on these. And we can see the lamination in the sedimentary unit are persisting in the dolomite crystal. So it's really the replacement of albitized rock and that form these large. Nice geological curiosity and also on fluid reaction, how you can really change the picture of the rock just by replacing it. That's a very fascinating example. And then as we move towards scattering or the rich component of the system, then chlorite starts to get in, and the carbonate composition is going to switch from ferro and dolomite to anchorite as the iron in the system. And then progressively, the rock's going to get replaced by that chlorite to the point of becoming green rock, and then native gold can be present within that chlorite. There can be different mineralogical expression of the iron-rich alteration. So certain times it's going to form pyrrhotite, so iron sulfide, and especially closer to the Espanola formation, it's going to be iron magnetite. And then some classic example of mineralization at scattering on the right side. So native gold sitting in chlorite. Sometimes the earlier dolomite crystal will be replaced by pyrite, and then there can be native gold in relationship with that. All over printed albitite. And then on the left image, so this is an albitized and then chloritized Sudbury breccia in a glade. And same processes at scattering. So we have the relics of albitite, and we have this chloritic front that came in and replaced Sudbury breccia and then deposited native gold in the process as well, forming a mineralization assemblage that is very comparable to scattering at glade. Just in this case, the whole Nipissing cell instead of being serpent quartzite. And when we move to the apical part of those systems, and this is what helped us vector in at glade as well towards deeper zone, potentially establishing the relationship with scattering, that when we move to the edge of scattering, so image D here, we can see that massive chlorite or the strong physical alteration is going to transition to a chlorite quartz assemblage. You can see that it comes with native gold. And then at glade, we started observing the same thing at surface, these vein of quartz with chlorite, sometimes with native gold. So that was somewhat suggesting the association with scattering. And by seeing the chloritic alteration with native the Sudbury breccia really demonstrated this relationship. The Espanola limestone is still quite altered at both locations. So below scattering, the Espanola can be replaced quite significantly by magnetite. And at glade, there's diffuse, but sometimes relatively pervasive gold mineralization in the Espanola. Visually, it's not very obvious for certain of these samples. Sometimes it will come with the iron-rich alteration, but other times it will come with very fine dissemination of sulfides on the lamination, the limestone of the Espanola formation. A target that has been well known or what its special extent is in the southern province because visually it's difficult to see. We picked it up in channel samples by luck, I would say, and also by drilling, by extending the holes in the Espanola formation. But there's potentially much of that in those limestone. It just needs to find where. Another style, I'll be interested, cobalt mineralization. There's 4 main areas where we have seen this mineralization: Alwyn, Long Trench, Powerline, Jove and Palkovitz, and the Bristol breccia, which is just west of Scadding. 2 different visual expression. One is dissemination of pyrite and brecciated albitite, and the other one is dissemination of pyrite and albitite without necessary radiation. So when we have this and when it occurs as a breccia, these are an example on the right side from scattering. So we have the albitite. It gets brecciated by this quartz and dolomite alteration. and then can be a progressive infiltration of pyrite with that. And with this infiltration of pyrite will come gold and variable component of gold in relationship to that gold. On the left side is Bristol breccia, which is like units of scattering. So we can see the albitite elementary unit brecciated, and there's a diffuse infiltration of pyrite with gold and some cobalt. For the replace albitite, so these ones are visually a bit more difficult. So on the right side, we have the albitized conglomerate, just the Alwyn area. The micrograph images are helping a lot. So if you look at the sodium, you can see that the rock has a pervasive content in soil. And with the disseminations of pyrite, we can start to see coming in as well in relationship with iron. So we have this albitite, and there's a potassic alteration infiltrating that albitite, which is related to this mineralization. At Palkovitz, we can see the same thing, but more intense. So we have this sedimentary unit. It's a conglomerate, but I'm not sure which formation. Near the Grenville front, the formation are a bit difficult to recognize. But we have this front of silica alteration that came in. And again, with the infiltration of potassium, which is seen in green on the image, you can see there's a network of potassium overprinting the albitite. And then there's this diffuse dissemination of cobalt that forms over this albitite. It's also another mineralization style that exists on the Sudbury project. And now that is interesting right now, also makes a relationship with other MIC system, is hydrothermal nickel copper mineralization. So this is located very near Grenville front. It's called the limestone showing. This was targeted because it formed a very significant anomaly. So it's a strong conductor, resistivity low. We targeted the edge of the resistivity low, and we were able to find a grade at this stage, but hydrothermal nickel mineralization with some FPGs is the geological control location of that is probably a limestone that is in the geological formation as well. And when we look at the mineralogical assemblages of what we can see, so we have a paragenesis which is made of variable apatite, pyrite pyrrhotite. In this case, the iron are replacing the oxide. If it was iron oxide, it would be iron oxide apatite type of assemblage. And then with that, we have some nickel that's coming in as well in relationship to the development of that alteration type. And just adjacent to that, there's zone of very intense magnetite alteration too. So if we start putting those back in the framework that we have from IC system, and to understand which component of the systems we are observing on the East Sudbury project, so we can see that the original component, the sodic alteration, is present. We do have indication of hydrothermal nickel mineralization associated with high temperature calcium iron alteration type. Indication of mineralization iron silicate, in this case, primarily, it seems, of gold mineralization at Alwyn, and then enriched gold, and then diversity of iron ore type of mineralization, or in general, printing zones of sodic alteration. So when we think about this and what's going to be some of the key next steps in order to try to vector and also identify zones that could have a good potential to host a large concentration of metal. So there will be a airborne gravity survey that will be conducted over the East Sudbury project. The gravity survey can have two advantages. The chloride associated with gold that's inlaid is not responsive very much to geophysics, but if there's a concentration of it, a gravity or residual gravity could be able to pick it up. And same relationship with Alwyn. If these zones of iron silicate with copper and gold are forming or accumulating on a large scale, a gravity survey should also be able to pick up those zones of alteration. Also, out of a collaboration with the Geological Survey of Canada and Natural Resources Canada for the Critical Mineral Initiative, there will be a seismic survey conducted over the McLaren Lake Fault in the Alwyn area. The seismic survey will be quite interesting because it's going to be able to map at depth the extent of the lake fault, so really understanding the scale of that structure, but also it will be able to find a fracture network because it's going to utilize fiber optics as seismograph and be able to provide a relatively high resolution image of the fracture networks that exist in the geological environment. So in order to define the zone of enhanced shattering where maximum fluid flow could happen, this could be a very good tool as well to vector in exploration in the next step. And the integration of those results or the seeing what the seismic survey is saying with the other geophysical surveys will certainly help to refine target definition in these areas. So I'd like to thank you for the association for the invitation to present, and thanks everyone for listening to the presentation.